Welcome to the second section of this course, Accelerating Hashtag Processing. In this section, we will go through an introduction to the concept of parallel processing, and in respect to programming languages, to the concept of multithreading. We will learn about the different options of performing multithreading in Java, such as using the Executor service. Finally, we are going to leverage this knowledge in our Twitter client application to process multiple hashtags in parallel. Now, let's proceed with the first video in this section, Introduction to Multithreading in Java and the Executor service. In this video, we are going to look at explaining the concept of multithreading, then showing examples handling multithreading in Java, and finally, we will diversify the examples by going through different approaches that we can take to perform multithreaded operations in Java. First of all, we need to define a few concepts around the topic of multithreading. For example, if we're talking about concurrent execution or concurrency in general, we are talking about executing tasks in parallel. Further on, multithreading for a software developer represents launching multiple parallel threads inside an application. The main benefit of parallel execution is better utilization of processing power. But please bear in mind that while parallelizing tasks can improve performance, multithreading is not always appropriate. We will explain this in detail in the next few slides. There is a subtle difference that you as a software developer have to understand between a process and a thread. A process is an entity managed at an operating system level. When you start a new application, that will create a new process. A thread, however, is managed at an application level. Both processes and threads can represent blocks of code executing in parallel. However, there is a key difference from a memory perspective. Two threads inside the same application can share memory. All the memory elements, such as variables defined at an application level, are available to all running threads belonging to that application. The memory for processes is completely separate, and by default, two processes do not share any memory. Let's take as example a single threaded application that has to read 3 files sequentially, count the lines in each file, and display the results on the screen. In the single threaded application, if reading the files takes 2 seconds and counting the lines takes 1 second, then the whole process will take over 9 seconds. While the files are independent, the reading of those files can only happen in one instance at a time. By comparison, in a multi-threaded application, we can add the 3 file reading steps in parallel and do the same with the blocks of code counting the lines. Since these are now happening in parallel, the duration does not add up. Instead, we reduce the overall execution time from 9.1 seconds to 3.1 seconds. This slide exemplified the right situation when we should use multithreading. There is no hard rule enforced in Java, and it's up to you as a developer to decide. And that's why you must know when is it appropriate to use this feature. The JDK exposes a rich API for handling concurrency in a few ways. The concurrency package has been introduced in JDK 5 and has evolved since to help developers cope with almost any multithreaded requirement. The package contains many interfaces and classes, and for a complete list with explanations, you can go to the official JDK documentation. In this video, we will go through the most commonly used objects and provide examples on how to use these. Callable, for example, is an interface that describes a task which may return a result. Therefore, as you will see in the next few slides, its implementation will have a return statement. While not trying to jump ahead in the list, in contrast, Runnable is very similar, but without returning a result. It is only meant to execute a block of code. The Executor service is a class which exposes functionality around scheduling, managing, and terminating asynchronous tasks. The future object is the result of an asynchronous operation. For example, you will get a future object after submitting a new task to the Executor service. Another useful class, Thread Factory, is one way of creating threads on demand. Starting with the Runnable interface. As mentioned on the previous slide, it represents a task which is not meant to return any result. To create a new Runnable instance, we have to implement this interface, and as you can see in the code snippet below, the code required to do this is fairly simple. What this block of code does is declare a new class, myRunnable, which implements Runnable and therefore has to implement the run method. Then we create a new thread with our class and start it. In a very similar fashion, when we look at the Callable interface, the main difference is the fact that it returns a result. Otherwise, it is the same. It has to be implemented by the developer as a new class and submitted for execution. This time, as you can see in the code snippet, we are submitting it to the Executor service to get a feature. The code until here is non-blocking, which means the execution of our Java process will not stop, even if the callable thread takes a long time to complete. Then, when we are trying to get the result of the feature object, we will encounter a blocking operation. The execution will stop here and wait until a result is available. This example is touching on two more concepts we've mentioned in the list of APIs, but don't worry, we'll look at these individually in the next few slides. The future interface is describing the result of an asynchronous task. If you're familiar with such concepts from different programming languages, such as JavaScript, you may know this type of object as a promise of an operation. It does not contain the result, but it provides the API to wait for it and retrieve it. The code sample on this slide shows you how an Executor service returns a feature of the type string as a result of the callable submission. From the type of the feature, that is string, we can infer that the return type of the callable is also string, since the two values have to match. And we finally reach the elephant in the room, the Executor service interface. If you develop a multi-threaded application in the proper way, it's highly likely that you will be using the Executor service as the main component, which is handling your multiple threads. The API that the Executor service interface offers allows for a few operations. First of all, by creating a type of Executor service, we are essentially creating a new thread pool. Then, we are able to submit or schedule new tasks, which are added to an internal queue and only executed when the threads are available for this purpose. The API also allows for either a gentle shutdown, when the Executor service waits for all threads to complete and stops accepting new threads, or a forced shutdown, where it tries to kill the threads. On this slide, you can see 5 different types of Executor services, or specifically 5 different types of thread pools that can be created. The first statement creates a cached thread pool, which is able to reuse existing threads to improve the performance for applications submitting a large number of threads. Next, the fixed thread pool is the classic choice for most applications. The developer specifies a maximum number of threads, and without any more specific functionality, the Executor service does the job. The third option, the scheduled thread pool, is probably the most advanced in this list. It not only allows submitting tasks for execution, but it also allows scheduling tasks, either after a certain delay or for repetition. The single thread executor is well defined by its own name. It creates a thread pool with only one thread available. This means that the order in which the tasks have been submitted is the order in which they get executed. The work stealing pool is a new concept introduced in Java 8, which allows threads to steal resources and use each other's time if one thread's work is completed. Each of these options comes with its own benefit. And if you'd like to learn more and make sure you're making the best decision in your application, please feel free to visit the official JDK documentation at docs.oracle.com. As you already know, a core concept introduced by Java 8 is the Streams API. We have used it so far. A detail which we have not dived in yet is that the stream interface supports parallel streams. A parallel stream exposes the same API as the standard stream, but can run operations in parallel. Behind the scenes, this uses a standard fork join thread pool, where the thread limit is one less than the number of processors or cores on the machine. You can see how the Streams API specific syntax is still used, with methods such as map and collect working in the same way, with the only difference that now the map operation happens in parallel. Please bear in mind though that using parallel streams is only recommended for operations which can take long time. In the current case, where the map operation will take milliseconds at most, creating the threads will take more time than the actual map operation, therefore cancelling any benefit given by the parallelization. Use this function wisely. Finally, for this video, it's worth mentioning some of the common problems that can arise from improper use of multithreading. One common issue has to do with two different threads accessing a variable in the same time. There is a risk of both updating the value of that variable in an undetermined order, therefore yielding to a non-deterministic result. Deadlocks and live locks are also potential issues and describe a situation when multiple threads are waiting on each other and therefore none of them is being able to complete. We will go deeper in these topics in future videos, so there is no need to learn them now. Just knowing that they exist will be sufficient.